Clarifications corner. I'm not actually going to do anything. I intend to just talk into the microphone for a while, so feel free to skip. But there is a little bit of a rant I want to go on, and there's nobody here to stop me. So last time we did robot racing. We focused on robot racing, and there was a whole bunch of improvements that we did. We built an ASIC, and this is pretty efficient. I'm not actually going to talk about robot racing itself. I'm going to talk about a thing I mentioned in passing last time, and since then I realized this was an instance of a much more general thing, which I've kind of been ignoring so far, and I wanna bring attention to it and just talk about it for a bit. So if we take a look, doesn't matter what actually happens here. If we take a look at this component right here, it's called 3+_b4, which is great naming, I know. But really what this is supposed to mean, this is a component that takes an input that is a base 4 number, so a number 0 through 3 encoded in binary. And what it does is it adds 3 to it, right? If we take a look at how it's implemented, it's actually remarkably small, right? It's just a NOT and an XOR. And I did this last time, and I'm pretty sure I showed it off, and I said I was pretty happy with how tiny this turned out to be. But what's interesting here is the fact that this is not actually implementing any kind of logical structure that I would myself call addition, right? There's no adder here. There are no constant adders here, wherever they would be. These things, which I've been using quite extensively in a lot of places. I've developed a whole theory of constant addition in binary. But none of this is happening here. I am not doing 3+. Instead, what happens is I'm working with pure bits. I just have a NOT and I have an XOR, and really I never even thought about what it means. What is, if you will, the semantics of these gates. And this is an interesting thing. The way I actually came up with this is I realized that this is a fairly small component. I only have 2 inputs, right? If I only have 2 inputs, this means there's a finite, and a pretty small for 2, a finite number of combinations that are even possible as my inputs. And what I did is, this is literally what I did. I just drew a truth table for this component. So we have options of inputs. If our input is 0, 0, right? If they're both 0, then we have our input as the number 0. What we need to do is we need to do +3. So the outputs need to be 1, 1. That is a 3. Next up, if our input is 1 +3, we need to get a 4. If our input is 2 +3, that will be a 1, right? And if our input is 3 +3 means a 2. So I literally came up with this truth table. And what I noticed is, well, first of all, the first bit of the output, this column right here, corresponds to the top, corresponds to this output, right? It's literally, if we just look at the bits without thinking of what it means to add 3 or add 1, just looking at the bits, what I realized was this thing is a negation of this thing, which this thing is going to be the first input, this here thing, this one, right? And the same thing applies to this XOR. Once we have this table, once we have this column and we have the other input, this one, we realize that XORing these two together gives us this column. I'm not gonna go into the detail. I'm pretty sure you can see it for yourself. So in order to build this constant addition of 3, I did not even think about addition, really. I did not think how addition works. What I did was I just looked at the bits and I was able to come up with a circuit. Now, obviously, this idea is not new. This idea is not even new to me. I am well aware that truth tables exist, and in general, I am well aware that the problem of building an implementation in gates starting from a truth table is a general problem in, I mean, computer science, circuit design. I'm not sure what area this would be, strictly speaking, but yeah, I'm well aware that this is a thing, that this exists. And I'm aware of logical formulas. I am aware even of things like kernel maps and the Quine-McCluskey algorithm for this exact purpose, as well as a bunch of others. But what I really wanted to bring attention to, if that's a phrase I can use, what I really wanted to mention is I've kind of been ignoring this so far. And I think this is an important thing to keep in mind, that especially for smaller circuits, what I can do in order to optimize them is I can just think of them in terms of bits, just stupid binary relations. This idea really captivated me for a while. In fact, it still does, but we'll get to that. The idea that given a truth table, there exists an algorithm using which I can build, first of all, I can just build a circuit. That is always the case. It's pretty simple to build any circuit. But even more interestingly and more importantly, given the truth table, there is a possibility to come up with the most efficient implementation of that truth table that is at all theoretically possible. There is, for any truth table, the solution with the lowest gate score, and there is a solution with the lowest delay score possible. And this is just fascinating to me. This is very interesting. I would like to be able to do that. Now, I understand that this is an incredibly hard problem, both in terms of, human understanding, so far as I can tell, and kind of more importantly, this is an NP hard, I believe, problem. So it's even more difficult than NP complete, which basically means no, you're not getting any results ever. But still, for small inputs, I have for a while been considering trying to either find somewhere or come up with my own algorithm that would, given the truth table, produce the most efficient implementation of that truth table in Turing Complete. Long story short, what I'm here to tell you is I eventually decided against it. It's not that I am giving up, it's not that I'm saying it's completely impossible and that I'm never going to do it. But it's just, I decided that it was way too much effort, way too much time expenditure even, in order to write a pretty minor optimizer for a game. And I don't see much merit in it generally. So yeah, in the end, I decided against it, but I just wanted to talk about a couple of things I realized in the process. My first encounter with this general idea was actually all the way back in part 15 of playing through Turing Complete. And this was back when I was trying to solve the Steam achievement, which required me to build an XOR gate out of only 4 NANDs. And well, what happened back then is for some reason, this looks pretty simple, but for some reason I couldn't come up with it myself. And I didn't want to look up the solution online. So what I did was I wrote a quick script that basically generated all possible combinations of 4 NANDs, which this was a bit weird, but I'm not gonna go into it. It's not actually 4 NANDs, it's strange. But the important part is I was able to brute force this based on just the truth table. I did not explain to it what an XOR was, air quotes. All I did was I told it that an XOR is a thing which has this truth table, right? False, true, true, false. And I tried all possible truth tables, all possible combinations of NANDs, and I found one that fit. And that was it. So all the way back here, I have already considered the basic idea of trying to come up with circuits from truth tables. However, when I tried to generalize this approach beyond just NANDs and then XOR, when I tried to make this a generic solver for any kind of problem size, I realized that this basically is not feasible because the number of combinations that you would need to go through with your brute force algorithm just explodes. And long story short, this is not feasible. It's just not going to work to design anything of any kind of size that will be better than just me looking at it and trying to come up with a thing using my own brain. So yeah, this is just not an approach that can work. So naturally, I turned to more established, smarter approaches to the same problem that would be more efficient than just my brute force algorithm that was completely not feasible. Of those, the only thing I was really able to find, and I think this is pretty much the be-all and end-all of them, is Quine-McCluskey algorithm, the method of prime implicants, which you see right here, method for minimization of Boolean functions, and, well, this is itself incredibly computationally hard to the point of requiring heuristic methods. However, even so, even if I were to apply this, this actually does not get me all the way there. Not for Turing Complete, definitely not for Turing Complete. And there's kind of two main problems with this. The first one being, how do I show this off? Well, I can't quite point to anything in particular, but the important thing is, this method only works for minimizing a single output from a component. So for example, you can see right here, it's FABCD equals some expression, but it's not FABCD and GABCD equals some other expression. It's just one output. And what this corresponds to in Turing Complete is, if I were to try to optimize this thing really has two outputs. There's this output and there's this output. And what Quine-McCluskey allows us to do is it allows us to optimize this one separately. So we can build a circuit that takes these four inputs and optimizes this one output. And we can also build a circuit that takes these four inputs and optimizes this one output. But it does not optimize them jointly. It does not optimize the aggregate output of this whole component. And that is a problem, because in order to optimize the two at the same time, you do need to take into account the fact that they are optimized jointly. And this is problem number one. Problem number two is the fact that all Quine-McCluskey really does is it gets you to a standard representation of your logical function, which is this right here. This is a sum of products. So basically, all it does is it tells you a combination of ands and ors, which you can use to represent your function. And this has two issues. First of all, this does not take into account other gates that we have. So we also have NANDs, we have NORs that are basically free to us, right? They cost no more gates than ands and ors. They're one gate. And it is not entirely clear how to jump from this to that. Even more importantly, Turing Complete has switches, which, so far as I can tell, are not actually part of conventional real-life circuit design. There's no such thing as a switch, and really nobody works with switches. So that would be another whole huge complication, which is not taken into account at all by any existing algorithms. And the third part, which kind of lumped them together, but the third issue with this is the fact that it doesn't do what I would call common subexpression elimination, probably. Like, if you take a look right here at this expression, what you get, this is your optimized output, right? You get not D here, and you get not D here. So A, B, C, D are inputs, and this is our output as an expression. But what it didn't do is it didn't tell you to save D prime, right? This is a not D, which in Turing Complete, I would have an input D, right? This is D. I can't draw a D, whatever. And I not it once, and then I can use it twice, right? I can use it here and here. Instead, what it tells you to do is it tells you to use two nots. It tells you to use a knot here and a knot here, and it tells you to put them like so. So that's another thing it doesn't do, and another thing I would need to do myself. Long story short, again, I considered a couple of options. This is interesting, this is still interesting to me, and I might at some point decide to do this side project of creating a Turing Complete specialized, provably perfect logic minimizer. But it's just way too much work. It's way too complicated. I can't justify it. However, there do exist implementations that have been made for us. There do exist logic minimizers and circuit design helpers that have been written by very clever people that use heuristics, that use the aforementioned, whatever it was, espresso heuristic logic minimizer. And I can, instead of writing my own, I can use theirs. And that is what I intend to do from time to time. And this is kind of the result of all my search and all my thinking about these things, is I want to tell you that I intend to, from time to time, cheat and use a logic optimizer to improve my circuits. And immediately I'm going to apply one to improve this circuit in particular. So meet Logic Friday. Of all the things I was able to find, this one seemed to be the most intuitive and to produce the best results. Which is kind of weird because this is actually an outdated, no longer supported program for which the website is not even online. I had to pull it off the web archive, and this is a old Windows executable which I'm currently running under Wine. So it's quite strange in that regard, but still it seems to be producing the best results. And well, at least this is one I could figure out how to work. So yeah, this will allow us to do exactly what I just explained. This will allow us to input a truth table, and out pops a formula and optionally a circuit with actual gates that will just need to be translated into Turing Complete format. Now, there's actually still a question here of what exactly do I want to use as my truth table? Because, of course, there's a lot of things here. I could say that the entire circuit is a truth table with 6 inputs right here, right? I keep the counter counting, but let's say we have 6 inputs and we have 2 outputs, and I can optimize that. In fact, just out of curiosity, I'm not actually going to use the result, but there's an option to import truth table, and I built a truth table for this entire component using my Python implementation. So this is hilbert.csv. Here it is, right? So we have 6 inputs and 2 outputs, and that's all pretty much just hard coding all the directions in which the robot will need to go, right? And this is what we get. We get our truth table on the left. You can't quite tell that it's a truth table, but trust me, it is. And on the right, this is just the basic formula for that truth table, which we can now minimize. We can press minimize. We can say exact and minimize jointly. I'm not actually entirely sure what these mean, but these seem like good options. So yeah, I think jointly is the thing I talked about here, right? Not minimizing each one separately, but minimizing everything. Exact, no idea. And besides, like I said, this will not be able to actually optimize to perfection in Turing Complete because it doesn't have some features that Turing Complete has. But still, I can press OK. It minimizes it. So this is already a bit smaller, right? This is a slightly simpler logical formula for this truth table. You can see some of the values became x's, which means don't care. But further, what we can do is we can say map to gates. And I can select the gates I want. So NOR, short 2 in. Let's just use everything that's 2 inputs. So AND, not sure what the mux is. I assume inverter is not. Yeah. And I press OK. And now it pops this monstrosity. Which, oof. Zoom in. Yeah. No, zoom out. Yeah, how large is this? Yeah, 68 gates it looks like, right? This is a tiny 68 over here. It counts them. So if I were to directly translate this to transfer this into Turing Complete, which I'm definitely not going to, this would cost me 68 gates. And what's the delay score on this? Let's just do a quick estimation. So let's say 1, 2, 3. It looks like, no, it looks like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Let's say 12, 13, 14, 15, 16, 17. So roughly 17 gates long. So that is a delay of 34. So 68, 34, it looks like this would be. How does it compare? Well, you can see that my delay score is better. Did I say 34? Yeah, my delay score is better. My gate score is probably a little bit worse. So 26. No, actually, my gate score is also better than this. So optimistically, I'm not entirely sure that everything's correct here. But optimistically, I can say that my brain was able to utilize the capabilities of Turing Complete, which is probably these muxes, I think, most likely, which are using switches, which is an important thing that this optimizer cannot do. It looks like I was actually able to come up with a better solution than this thing. So I don't even need to transfer it, but theoretically I could. Now, what's more interesting is instead of trying to optimize the entire thing all at once, what I can do is I can select a smaller subset of it that also has a set of inputs and a set of outputs. So for example, I could just try to optimize this 3+, right? I'm probably not going to because, well, this already seems pretty optimal to me. But even more interesting, instead of optimizing a single component, I can try to select some other subset. And the one I'm looking for, the one I'm looking at, the one I've been looking at for a while now, is this part here. This has 4 inputs, right? This has 2 inputs for the number and 2 inputs for control flow on the number and 2 outputs. So that's a pretty small truth table. This is going to be 2 to the 4th. Rows and 2 columns of outputs. So that's a small truth table, and I think, considering how inefficient I am being here with this 3- and double muxage and all that, I think Logic Friday should be able to come up with a better implementation of this part here. So what I can do is I can click New Truth Table, and we're gonna set up a new truth table. So we have 4 inputs, right? These things. We have 2 outputs, so 4 inputs, 2 outputs. And let's name them for readability. We have white thing, this corresponds to flippage. This decides whether or not we want to flip our vector at all. So this is our input vector. Then something might happen or nothing might happen. And this is the mux. So let's call this flip. I'm kind of going left to right here because that's the more natural order. Next up, we have the yellow wire. Did I say left to right? I should have said right to left. Sorry if I was... whatever. Next up, we have the yellow wire. And what this does is it decides the direction of flippage, right? We have this direction of flippage and this direction of flippage, 3 minus or 1 minus. So we're going to call it direction. And then all we have is just the vector itself. So I'll call that input 1, input 0 corresponding to the most significant and least significant bit. Same thing for the output. It's a vector, so just output 1, output 0. Okay, ready to proceed with the truth table. It's kind of awkward this way. It folds everything for some reason to the point of not being even visible at all. Okay, so we are now creating a new truth table, and what I can do is I can flip these bits just by hand. When we are not flipping, so this part, flip equals 0, what these values need to be, the output needs to be the same as our input. So O needs to be the same as I, so 0, 1, 2, 3. Again, 0, 1, 2, 3, no problem. Next up, we need to flip, and this time we're actually flipping. But when we're flipping, we have our direction. If our direction is 0, then what we're doing is an operation that is 3 minus. So we have our input, it is 0 right now. 3 minus 0 is 3. Next up, 3 minus 1 is 2. 3 minus 2 is 1, and 3 minus 3 is 0. So this is our flippage in the first direction and the 0th direction. And then the other direction is going to be not 3 minus, but 1 minus. And what we have is 1 minus 0 is 1. 1 minus 1 is 0. 1 minus 2 is going to be 3. 1 minus 3 is going to be 2. Right? Because modular arithmetic. So this is our truth table. I just, as you can see, entered it manually. I press enter. Here it is. Here's the base unoptimized formula for it. We can press minimize again, exact, smallest number. Yep, this minimizes quite a bit. Looks like quite a nice minimization. And I can press map to gates. Same thing, I'll select all the double gates. And we'll press OK, and boom, there it is. This is the component that implements the same truth table as my custom component, except it's optimized. These things are not labeled, but they actually correspond to the appearances of the gates in Turing Complete, or rather I assume Turing Complete was built to correspond to standard logic circuit notation. So this, for example, is a NOR, right? You can see it's this shape, and then it has the circle at the end, and you can kind of make it out here on the NOR. So these are two NORs up here, and down below are two XORs. I believe. Yeah, these are two XORs. Right? So now all I need to do is I just need to create a custom component that implements this. And I'll be right back. There we go. Here's my new circuit. Now, instead of the huge thing, I just have a little flip component that has a gate score of 8. So fairly cheap. Just has two XORs, NOR. Well, this is the same, pretty much the same thing you saw here, except I moved some things around. This thing is a NOR with a 0, so it's pretty much just a NOT. So I replace that, and other than that, it's the same circuitry. And we can test whether this works. And in fact, it does. And now we have a score of 161. which, if you recall last time, my original, this solution, had a score of, let's see, 171, and it was actually beat by the absolutely trivial cheat solution, which was a program with all the steps hard-coded. So if we run this, I believe, yeah, what we get is 165. So this was better than my original, which was kind of, it kind of hurt. But now, with my fancy optimization, 161 is the final score that I get on my ASIC. And it's better than the dumb program hard-coded solution. So I'm pretty happy with this. Like I said, there might be other optimizations. I might want to try to combine the mux with the flip, you know, have these however many 7 inputs and 2 outputs. Or even more likely, I could try to use this, right? All that happens to the vector here is this component here, the 3+. So I could also make 3+ a part of flip and also feed that to Logic Friday. Between us, I actually tried that, and it came up with a weird sort of, I'm not sure how efficient it was, but it was a weird spaghetti, which was strangely large. So I decided against it. I'm not sure how Logic Friday works exactly. So yeah, it's not a, it basically doesn't have final say over what I'm going to do, and I'm just gonna go with my gut on these things for now. And yeah, I'm gonna say that this is my solution. The 3+ stays. Logic Friday wasn't able to optimize beyond it. It was only able to help me with the flip. So yeah, that's it for Hilbert. And now I'm ready to proceed with next parts of what I intend to do for this video. That being a Steam achievement. I believe this is the last substantial, non-hidden achievement I still have to complete in Turing Complete. I got all the rest. And that is the fast adder. Complete the byte adder with a delay of 35 or less. So it looks like what I need to do is implement, is this it? No, adding bytes. Implement this thing with a delay of 35 or less. And my current delay is 80. So that looks like quite a challenge. That's less than half of what I currently have. My original byte adder is the very simple basic design that is common for a lot of 8-bit components. It's just basically incorporating 8 copies of a 1-bit component, except this one, of course, has a carry line, which I expect this carry line is really the culprit to my delay score. Yeah, definitely. This is the very long delay line, yes. Okay, so that is exactly where we get our 80 from. We have 8 copies of these. Each of them is 10. They get summed together, and that's how we get 80. Okay. Before I really dig into this one, I think it would make sense to start by actually examining the small adder itself. Maybe there is some improvement I could make in there. Now I doubt I can reduce this to, what would I need it to be? It needed to be 4, right? I would need to reduce this from 10 to 4 delay in order to just keep my byte adder the same, but reach the achievement, complete the achievement. I don't think I can do that, but still, even a small reduction, maybe from 10 to 8 or to 6 would be great. Even a small reduction could potentially help me. So I think I'm gonna go back to the full adder and take a look at this one. So far in this playthrough, I haven't really concentrated on the delay score at all. I've mostly been concerned with gate scores. I think it's just because a gate score is the very obvious thing you can immediately see when you look at any circuit. It's just basically the size of your circuit, right? How large it is. As opposed to the delay score, which is a lot more subtle, right? You can have a huge circuit with a very large gate score, but a delay score of 2, right? If you just have a million things running in parallel. And kind of vice versa, you can have a huge delay score, but a pretty, well, actually, no. In order to get some delay, you need some gates, so... No, I think the gate score must be at least delay score halved? Yeah. I think that's right. But doesn't really matter. What I was gonna say is I haven't really figured out a lot of tricks with regard to delay score, and I haven't even, thought about the theory of it all. The general statements you can make about delay score. The one thing I do remember is the switch trick. This I did figure out for some of my ASICs. And I think I even mentioned it at some point, that basically anytime you have a chain of ORs, if I need to OR 1, 2, 3, 4 signals, right, that would be this structure in terms of ORs, and this would be a pretty large delay over this line, right? We'd have 2, 4, 6 delay, right? But instead, for these same 4 inputs, what I could do is I could use 4 switches. Oh, which I do not. Huh. That's curious. So at this point in the game, I don't even have switches yet. So that won't even matter. But just so I can finish my thought, what I can do instead, imagine these ANDs are actually switches. What I can do for 4 inputs is I can connect them like so, right, and then run this in parallel. Right, so these would be my 4 inputs, and this would be my 1 output, and that is in fact an OR of them all. And that saves me a lot of delay. Right, this would have a delay of 2. I wonder, now that I notice this, I wonder if maybe I have switches in the later level? Like where? Yeah, bit switch here. Aha, so I think it should be, yep. That's curious. So I do have switches for the large component, but I do not have switches for the small constituent part of it. So hypothetically, if I am able to apply switches, I still could here. But I think I still want to try to start with the smaller component just to get the hang of things a little bit, and overall I think it's an interesting challenge. So yeah, I'm gonna focus on this, and I'm gonna ignore switches for now, which I think will be useful in itself as well. Okay, so what do we know about delay score? It is the depth of my circuit. It is the largest depth. I'm not sure what this would properly be called, but actually, yeah, I think basically what any circuit is a directed acyclic graph. It's not a tree, because we do have things joining together, but it is like this is not strictly speaking directed, because wires run kind of both ways, but so long as we don't have switches and we don't have circular dependencies, we pretty much do have an order in which gates apply from the input to the output, and we cannot lead back into itself, right? So yeah, this is kind of the acyclic part, and yeah, the direction is input to output. And so what the depth is, I don't know how this is useful at all, because I don't actually know that many properties of directed acyclic graphs, but the delay score of my circuit is going to be twice the longest path in the graph. No, twice, just because for some reason, I still don't know why, for some reason delay score of everything is 2. So yeah. So here what we have is, wait a minute, why is it so, so XOR, XOR, and AND, that's our 10. I'm not trying to tinker with it yet. I'm just trying to think about approaches. And one thing that comes to mind, this is, so far this is just an intuitive statement, but just generally, in order to get the lowest delay score, what I want is I want the flattest circuit, and this is kind of intuitively also equivalent to doing as many things as I can in parallel. Right, so I don't know how to describe this, but yeah, I don't want depth, I want breadth, width. And what this brings me to think is, how about I consider my input and output. Okay, I want a new schematic. So low delay. How about I consider the input and the output of my, or sorry, the either output of my component to be completely separate. And I build a circuit up top that optimizes for delay score on this one. I build a circuit that optimizes on this one, and they do not intersect. So this line does not, nothing crosses this line. This is going to be, this is definitely going to be at least as efficient in terms of delay score as a single component that, that doesn't do this. Simply because I can easily prove this. I can just take my combined component and I can, this might be a good starting point even. What I can do is I can paste it twice, right? Because at this point I don't care about my delay score or my gate score, so it doesn't matter. I am allowed to do things in parallel even if it costs me some gates. And I can just connect everything up. Just like this. And this is already giving me a circuit with my new form. But it has the same delay score, because of course it cannot have a larger delay score. And it still does the exact same thing. Right? Excuse me? Excuse me? What? Wait, what? Oh, simple mistake right here. Wrong input. So now this should work. Yeah. So it's still the same thing, except now it's separated into two. And here, my thinking is, because these are kind of simpler patterns, right? This is 1 bit, so it has fewer combinations, fewer possible truth tables for it. This is an easier computation to run, I don't know, I think there must be an information theoretic formalization for this. I don't know. But just intuitively, building two things at once, a joint configuration of these two things, is going to be more complicated than building one and building another. So perhaps, by trying to reduce them separately, I could come up with a better delay score. And I'm not worrying about gate score at all for this. And then actually, once I have my optimal delay score, I can Take a look at the two sides, and notice common patterns in them, and do common sub-expression elimination. Yeah. Okay, so let me just reduce this very simply. So I remove this XOR, and I'll just remove the junk. Okay, so my top half now only has a delay score of 4, and my or a delay score of 8. 2 times 4, 2 XORs. This is going to be 8. And so my bottleneck for reducing my delay score is now the bottom. So what I can do is I can try to focus on the bottom and simplify this somehow. And I think this might be even good to just because this is so simple. This is a single output. I think you can just take a look at the bit patterns, and yeah. So this is gonna be my carry, and what I want is, so I want this one bit. That's input 1 and input 2. And actually, when I have both input 1 and input 2, input 3 doesn't matter. Oh, I'm kind of running a kernel map, I think, in my brain. So, yeah, when I have both input 1 and input 2, it's fine. So what I can do is I can do... Let's see. Let's just remove this, whatever. Input 1 and input 2. Right? And this is already sufficient to get me an output. However, I still need to encode these two ones. And what they are is input 1. Is that... I mean, this is XOR, but wait. Well, yeah, I don't have anything better than XOR, so I need input 1 XOR input 2, but I also need to remove these two zeros, so I need these ones, so it's input 1 input 2 XORed. I don't know, just whatever. Like so. However, I also need another AND. It's getting crammed, but doesn't matter for now. Okay. Yeah, I think this encodes what I needed to encode. I think this encodes my carry, and it has a delay score of 8, which is an improvement. So let's check this. Yeah. Okay, that's already good. Somehow I doubt I can get this to 6. Yeah, I don't think I'm getting this to 6 because of the top part. So this is 2 XORs. This is a total of 8. But this is addition. And I'm pretty sure just doing addition cannot be improved. I think there's a gate score improvement I can run here. The order of these two XORs doesn't matter. So what I can do is I can bring this one out like so, right? This should be fine. But now what I notice is this XOR is an XOR of 1 and 2, and this XOR is an XOR of 1 and 2, and I can get rid of one of them. And yeah, I can just run this down or run that up, breaking my rule, but that's fine. Yeah. Let's check if this still works. It does. Oh, that's pretty cool. I'm pretty happy with this, actually. I think this is better than what I had. Yeah, this is better in both delay score and gate score. But still, I don't think... See, it kind of hurts me that I do not have my provably perfect solver. It just... man, it seems so close to being easy to implement a brute force algorithm for the provably perfect solver. But it just wasn't for me. I don't know, something was wrong. Something's wrong with me for that one. Maybe I should feed this to Logic Friday, but then again, Logic Friday does not optimize for delay score. I don't even know exactly what it optimizes for. It just does some kind of optimization, and I assume it's good. But yeah, it won't really help me all that much. Actually, wait. Yeah, no, these two XORs... I'm already starting to think about next steps. I'm already starting to think about using switchers and stuff. Because this right here, this construct or over here, I could do... Wait a minute. I just realized my large 8-bit component has its delay only from the carry line, and for the 1-bit component, the bottleneck is the sum line, but the sum line doesn't matter. It just goes in, sum, just immediately out, while the carries add up together through over all 8 bits. But if I were to unfold the adder in place, and even with this, even if I were to just use this, this actually has a delay score of 4. Right? And yeah, the carries will add up as 4 each. So I think I may have already solved the problem. Yeah, I'm just gonna jump into it, and I'm gonna try making it. I'm gonna try unfolding all my adders to this. In the large one. This is gonna be a bit of a wiring project, but I'll be back with the results. And a building block. So now I just copy this 1, 2, 3, 4, 5, 6, 7, 8 times. And I just need to split and connect. Like so. Yeah, I just realized I tricked myself. You must have been screaming at the screen, but it shouldn't have been a very long section of the video. Yeah, so we are down to 64, but of course, back when I'm not actually... Let's test if this even works. It looks like it does. Yeah, cool. That's actually a lower gate score and a lower delay score than I had, right? Yeah, 88 to 72 and 80 to 64. Yeah, back when I realized I could reduce the XOR, or reuse the XOR, I kind of tricked myself. I was still in the mindset of them being separated. Where is that? Yeah, at this point, I'm still in the mindset of this being the whole decider, the sole decider of delay score, but of course, it has a sneaky line coming in with this XOR, which increases its delay score beyond the 4 and up to the very 8. So yeah, that's unfortunate. I'm gonna have to redo all this. And I'm not yet sure how. It's still interesting to me whether I could get a pure carry line with a lower delay than 8. Would that be possible? Yeah, that's... If I could get a delay line that has a delay score of lower than 8, well, 6 still wouldn't be enough, as we've established. I would want a delay line with or a carry line with a delay of 4. I wonder if that's possible. So, oh man. Okay, let me think about this. Huh. I just realized something, and I think this is going to be especially useful for switches. Not so much for ORs, but with switches this is going to be super powerful. And that is sum of products. So any logical formula has a standard representation as a sum of products. There's multiple sums of products you can get, but the most basic of them, the least efficient, but the simplest one, is just you take a look. So let's take a look at desired carry. You take a look at every 1 in your output, and you just encode it as an AND of all the particular inputs. So for example, this 1 is going to be, let's call them, instead of 1, 2, and 3, so it's not as confusing, I'm going to call them A, B, C. And so this one in the carry is going to be A and B and not C, right? Then we take a look at the next one, that's going to be A and not B and C, so A, not B, C, or we continue not A, B, C, and the final one is going to be A, B, C, right? So this is the most basic sum of products representation of our desired carry. And again, letters just written together are ANDs, and pluses are ORs. Now, if I were to use ORs for this, I would need 2 ORs, right? I would need an OR and an OR. And I would need to join them together. And this would increase my, right? So I would have, this is an OR, and then those 2 are ORs. So we'd have a structure like this into a bunch of ANDs, right? Into 2 ANDs here and 2 ANDs here, which they are triple ANDs. And then there's some nots here and there. But the basics is this. Now, what I was going to say is, right here, these ORs, because they are chained, they cost me 2. But if I could use switches instead, I could save a bunch if I just had, imagine this is a switch. If I could just have this kind of setup, then the cost of my OR tower would be reduced. And actually, the cost of the OR tower is flat, regardless of how large my sum of products is, right? So I could have plus whatever, plus whatever, plus whatever, plus, 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 plus. Doesn't matter how many pluses I have, doesn't matter how many ORs. All of those are going to be essentially free. They're going to have a fixed cost of 2, a delay of 2. And that's actually very powerful. But now, I don't think this is actually the efficient representation of my sum of products for the desired carry. Yeah, it can be reduced. Really, we don't even need to apply anything fancy in terms of Boolean algebra or whatever. All a carry is a carry just designates whether or not we have at least 2 inputs that are on. So all I really need to test for is I need to have 3 ANDs, like this. And I need to test, 1. Is it 1 and 2? Is it 1 and 3? Is it 2 and 3? And then these I can connect using switches, the switch trick. And yeah, that would actually bring me under, or well, at a delay of 4, which should be sufficient. Okay, let me first build it here with the ORs. There. So, like I explained, 3 ANDs into a chain of 2 ORs. So this is currently separate and it has a delay score of 8. But, wait, is it 8? No, it's not 8, it's 6. This is currently 6, the delay score on this carry. But if I get rid of this OR in favor of a switch trick, then I will get it down to 4, and that should bring me over or under the line I need for the achievement. So just to really drive it home, what we have is this with 3 inputs. And what I can replace it with is, instead of using the ANDs, I can, well, that doesn't really matter, this is just for size. But these are basically my 3 ends with the same inputs. But instead of this OR construct, what I have is these one-directional switches, which have their input and output connected to the same thing. So it's basically, its off state is replaced with an inactive state with a gray pin. It feels like this is, what's the word? Superfluous? Super redundant? I don't know. Because it's kind of switches into switches, right? Why not just have it like this, right? But of course, this will not actually work because, for example, if I have this input on, then this switch gets enabled but is currently outputting off. But now, if I power, for example, this wire, we get a short circuit. Because now this switch is completely on, and well, it will be completely on, and it will also output the signal. So we'll have one red and one green. So that doesn't work, and I need to guard against it. And that's what these redundant switches do. Okay, so I guess now it's time for me to go ahead and just stack these on top of each other and build a new circuit with a delay of 4 on the carry line. And that should be it. There. This is a delay score of 36. Which kind of brings me to think this was probably intended. It looks like I got the optimal solution without applying some completely different new trick, which was the intended, the developer's intention for me to discover this new trick that will actually get me from 36 to 35. And the achievement is 35 or less. But yeah, this is applying the new switch trick. We have our addition line as normal. This is just 2 XORs chained into each other. I don't think that can be optimized. And now the carry is the way I explained. So we have a bunch of these. And actually, you may be asking, well, we do have 8 copies of these, and each carry costs me 4 delay, so that's 4 times 8, that should be 32. And how do we get 36? And the answer is, if we click here, it does go down the carry line, so this counts as carry, 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 carry. This counts 4, 4, 4 every time, but then, when we get to the bottom, the carry no longer matters because it doesn't go anywhere further. So this is just a 2, or this is just a delay of 4. While you could take the slightly longer path through the XORs and get a 36 that way. So yeah, that kind of screws us over a little bit. We cannot get to 35 this way, or to 32. So from here, I see kind of 2 ways to proceed. I think the first one is unlikely. The first one would be to just try to find some tiny little improvement somewhere. You know, maybe somewhere here at the end I can figure something out to get a reduction on these XORs, or, you know, just try to win a 1 somewhere, maybe at the start, or maybe, you know, just try to do some tiny little change. But I don't think that's actually going to work. And I think, yeah, I also obviously don't think that I can reduce my individual components any further. I seriously doubt it's possible to get the carry thingy to have a delay of 2. That's just a single gate, and there's no way I'm doing that in a single gate. So yeah, that's probably not happening. And the other approach is probably going to be something much more dramatic. It's probably going to be some version of applying the same separation idea, right? You know, remember this white wire splitting the circuit in half? Except now applying it to this larger thing with its 8 outputs. So yeah, maybe I need to calculate some outputs separately and then some other outputs separately, and that way I can parallelize it. I actually do have a particular thing that is just intuitively, that I'm just intuitively itching to do. And that is to try to carry out multiple kinds of addition in parallel. So the most basic version of this would be I take this whole thing, I copy it twice, right? So I have this and this, right? And then I know that there's two things that could happen. There's I could have a carry in, or I could have no carry in. And this would allow me to reduce this thing a little bit, right? An XOR with an on, an XOR with an off. These switches, this would reduce a little bit. And overall, the delay of this thing with an on should be a little bit smaller than the delay of the full thing. And then I get my outputs, right? I get my outputs from here and from here. But based on the actual input of my carry, I know which one I want. Do I want the on or do I want the off? Right? And I can decide. I can just have a switch, or, you know, effectively a mux, right? A switch here, and using this thing, I decide which of these I want on. So that's just the general idea, but this doesn't save me much. Like, at best, it saves me a little bit from here, and the overall delays is still pretty large. But this is a little bit naive, trying to copy the entire thing. What I could try to do instead is I could actually split it in half, split the actual computation in half. And what I could do is, I have my original. This does get its input. It gets its normal input. But at some point, and half seems like the best point, just intuitively again. So I do 1, 2, 3, 4 blocks. And then at this point, I stop, right? I don't carry any further. So now, this thing has its own delay, and this thing has its own delay. But in order to calculate this, I need an input to it, right? And I can apply the same trick. I can say, okay, let's calculate it with an on, and let's also calculate it with an off, right? I calculate the two of them, and then I apply the same trick. I have my carry out, well, I have every output, right? Each one of these outputs would need to be muxed. So I have a switch here, I have a switch here, and based on the carry, I know it's either on or off, and I decide, right? And the same thing happens to the carries at the end. So this would also need to be muxed with 2 switches, and with this carried all the way down. So yeah, you get the idea. And that actually looks like it should help me quite a bit, right? Because the delays get parallelized. I carry this out, and then this thing is the highest I get, and all further action it gets is just a switch, right? And then we're off to the output. And the same thing is true of this. It doesn't have a large tail coming in, it just has this on. And so this delay also just gets immediately to the output, so that's pretty fast. Same thing here. So yeah, I think this might allow me to cut it, well, probably not in half, because we're gonna have some overhead from the switching and the muxage and all that. We'll have some knots and everything. But overall, I think this is an interesting idea, which I am willing to explore. So I am going to implement this kind of structure, and we'll see what that gets me. And here it is. And it has a delay of 20. And I'm pretty happy with this. This is not actually, I'm pretty sure this is not the absolute optimal solution, but we're gonna talk about that later. For now, let me just walk you through this a little bit. It's exactly as I explained. So we have this thing that is just the regular adder. And then these two are its copies except with an on and with an off as its inputs, which I already reduced. So, you know, instead of a chain of XORs, we just get one XOR or one XNOR. And then every output bit gets muxed. So essentially these two switches, because I don't have a 1-bit mux, these two switches essentially play a role of a mux. And based on this white wire, which is the carry that we got as a result of our first half, we decide which side we want, right? Do we want the left side or do we want the right side of these outputs? And the same thing applies to the carry at the very end. And that's how we get our carry. So this is pretty cool. But like I mentioned, this is far from the absolute best solution possible. And in fact, I already tried an improvements on this, but it turned out to be way too much of a wiring job. You can't really copy paste stuff. It just takes a lot of manual labor, and it's very difficult to lay out, especially in this small box. You can see this barely fits, and further improvements are going to be even larger. That's actually an instance of the gate versus delay score trade-off, right? I am now using more gates to do more things in parallel, even though half of these basically don't influence the input anytime, at any point. So yeah, it gets pretty huge. So I'm not gonna do it. But I just wanted to talk about the general shape, which I'm pretty sure I have pinned down by now, of the most optimal solution to this level. And I think it's kind of fascinating. So yeah, I'm just gonna draw it schematically. So initially, our original thing, let's imagine this is kind of our just adder. This is just the shape of it. And what we have is we have this carry line, you know, running down, 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 all the way. This is just one carry line. Now, the first optimization pass that we already did was we split it into two halves, right? We take the top half of this thing. And then for the bottom half, we copy it twice. And we get this kind of shape, right? So now if we think about what the delay on this really is, what happens, right? Like right here, we have a single output and it just goes straight to the output, right? Over here, what we actually have is we have two outputs at the bottom, right? We have an output here and an output here, and they go into a mux. This is going to be a mux. I'm not sure what a mux looks like. So just imagine this is a mux. But that mux is decided by our carry output from the first half, right? And actually the largest delay on this is actually also when we put in the carries, the resultant carries from the two towers. So what we really have is this kind of situation. And now the carry out is going to be the result of this mux. Now, the delay on the carry out is going to be the maximum of the three inputs of the mux, right? So this is kind of where the even split comes from. If we were to have a large portion at the top and then smaller ones at the bottom, just imagine something like this, then we'd have a large delay here, and these two wouldn't matter. And we would have a larger delay at the end. So what we need to do is we need to do this balancing act. You know, this is kind of a pretty common pattern where in order to balance these things, in order to balance for the minimum maximum, for the minimal maximum, what you need to do is you need to take even parts and reduce them as much as possible. So that's how this works. Right now they have roughly the same delays. I'm just not gonna count all the infrastructure with the delays of the muxes and everything. Just in general, these are pretty much the same delay. But now, interestingly enough, what we can do is we can notice that all these three things are separate now, right? They're just connected through this mux. And what we can do is for each one of them, we can also decrease its respective delay. So what we can do is we can take a look at the first one and we can apply the exact same algorithm recursively. We can look at this stick right here and we can split it like so, right? Actually, let me make this neat by copying the same thing a couple of times, right? So it would look like this, and then we would need to apply the same algorithm to the bottom two, so they would look exactly the same as the upper one. So now we have this kind of shape. And again, they all get muxed together, so there's kind of a little mux here, there's a little mux here, there's a little mux here, and then all these three muxes lead to one big mux, and that's the output. Right, so then this is the maximum of those, and then each of these muxes is the maximum of those. So that's the shape. But now, obviously, we can proceed. And I'm just gonna do one more step, so it's really, really obvious. Come on, give me decent color. What the hell? Okay, just one more. When we split this thing into two, it's gonna look something like this, right? So then everything becomes similar to it, and this becomes our bottom. Do you see this? Are you seeing this? This is obviously a fractal shape, and in fact, it's a very famous one. If I can pronounce the name, Sierpiński, I think.
Wacław Sierpiński.
Sierpiński triangle. Sierpiński triangle. We all know what it is. It is, of course, this thing. Right? Do you see it? Do you see it? Do you see the pattern? I'm not gonna go any further, but yeah, clearly one triangle turns into three triangles, and then the bottom triangles also turn into three triangles the same way. And it proceeds this way forever. So yeah, it looks like in order to obtain the optimal delay on an addition of n bits, what we would need to do is we would need to build a Sierpiński triangle of order n for n bits. So yeah, what I would need to do here is I would need to halve this, and then have both of these, and then have one here. And same thing would apply down below. Yeah, and that would be a Sierpiński triangle of order 8 for my 8-bit addition. But, like I said, it's a huge wiring job. I'm not gonna do it. I'm gonna settle for a delay score of 20, and I hope I can catch the Steam achievement on camera. Let's run this thing. Yay! Got it. Great success. Nah, I just couldn't help myself. So here's this thing, copy twice to the bottom, and then this thing, copy twice to the bottom, and then, that's what we get. Now this is clearly a Sierpiński triangle. Oh man, I just realized something else I overlooked all the way back. Even at the half adder, this is already applicable. So remember how I said I wouldn't be able to optimize the XOR? Well, it's very much optimizable. and not even just the double XOR of the full adder, even in the half adder, this can already be improved. Because if we take a look at the XOR, it can actually be represented in two ways. Well, at least two ways. I can go back to my original XOR solution. No, this is not the original. This one. Yeah, so it's an AND of an AND and an OR. This is always difficult to pronounce. But there's an alternative way, which is, in order to get an XOR, I can use an AND and two NORs. So NOR, NOR. And this is another option I can use. So yeah. Again, this is just based on bit patterns. And while this doesn't save me on the XOR itself, it does mean that over here in the half adder, I can unfold this XOR, and inside it there will be an AND. And I can reuse this AND, and I can save a gate that way. Or another way you can look at it is this is just an XOR, but it so happens that inside of the XOR I already get the AND that I will need for the carry, right? So I build the XOR, I use it for the sum, then this AND I can reuse. And this is also applicable to the next problem. This level right here. And I think this is even going to be applicable twice. So for this XOR, it's an XOR of these two things, which is inputs 1 and 2, but we already AND them together. So what I can do is I can remove this. I can replace it with two NORs. So one NOR, but I will also want a second one. And then this AND goes in here, and then this NOR goes in there. But now, this XOR is an AND of these two things, but in fact, these two things are already ANDed in here. And I can also reuse this with the NOR trick. So I can put two NORs here if they will fit at all. Yeah, they do, just about. I'll clean it up later. Hello? Yeah. That's fine, whatever. Yeah, so now I can reduce the gate score on my full adder, and this is just the basic component, to 7, which is pretty darn efficient. See, I wonder if that's the limit now, right? Having improved it incrementally so many times by now, man. And thinking about this in terms of gutted XORs again, this is what that looks like. I just have this chain of XORs, which is necessary for the sum, but it so happens that both the ANDs that I need to have in order to get my carry are already present in this schematic, and all I need to do is to OR them at the output. How on earth am I going to incorporate that in here? Because I want to now. Although it won't actually really matter. I don't think, yeah, this won't bring me down below. Because, right, this is optimized for delay and not for gates. And I'm only saving gates with this NOR trick. And right here, I don't even need to. And in the original solution, this is already my optimal setup with 56 gates, right? Because this adder was now improved. Yeah, so I'm probably not gonna even bother with trying to implement it here. I'll just say that these XORs are fine, but importantly, what this means is that for all of my custom circuits, like, you know, base 1-bit constant adders, all of these, which are used, as you can see, quite extensively in a lot of my circuits, I will need to optimize all these because that will have pretty serious consequences, right? This adds up to a lot because it's used a lot. So yeah, I guess I'll have to go over all these. I want to end this one with a little bit of a cleanup operation. I have a couple of things I want to address. First up, this XNOR gate is just not right. This is inefficient, clearly. An XOR is expensive, and then a not for it is even worse. What we can do instead is we can have an AND, we can have a NOR, and we can OR them together, and that's going to be our fancy new XNOR. Like so. Improvement. Next, there's this RAM level, for which we currently use the entire full power of leg. And all this actually does is it introduces RAM to us, and it asks us to save 32 values and then output them. So this can be improved by quite a bit by just utilizing a small ASIC with a RAM component, I assume, because RAM is actually pretty cheap, right? Where's RAM? Wait, what? Fast RAM, latency RAM. Okay, so we have this RAM. Costs 256. Yeah, that's not a single register, will cost us 33. Yeah, so 32 registers will cost way more than a RAM. Although this does have a cost in delay score. I wonder if this could actually be an interesting thing to do in the future, to try to actually optimize this level by utilizing these different RAMs, like latency RAM. Maybe that would be more efficient. Yeah, I might do that next time. By the way, do leave a comment if that is something that would even be interesting for me to do. But for now, I'll just do the regular RAM, just so that I have the blueprint for it. There. This has a huge delay still, but yeah, this is pretty simple. I just made a specialized counter that counts up to 32, or well, 31 exactly. We need to load 32, and then we need to output them in that order, so it just overflows to 0, and then we start outputting. The way I detect that is when it reaches 31, then I know that I need to start output. So this is just a single cell that will keep its state forever. And I also need a delay because I don't need to output immediately when I'm 31. I need to output on the next tick. So that's that. The output gets enabled and we start outputting using the exact same counter that just overflowed. So let's run this and let's see what kind of score we get. Come on. Is this even any better? I mean, a little bit. I think it was 2K. And now we have 1373. But yeah, it's probably going to be an interesting challenge for the future to try to use latency RAM or something. Yeah, but I'll leave that for later. And the final thing in need of a little bit of cleanup is the stack level. This monstrosity. This has been long overdue. Now, of course, I already have a perfectly viable, whatever that would be, leg stack register. I have a perfectly viable and reasonably constructed stack, but I just want to have a clean solution to the original stack level. So I'll just clean this up. There. Hopefully now you can see why I was putting this off for so long. These used to be full adders. Those are pretty expensive for a plus plus and a minus minus, so I replaced them with this. That's because we don't have custom components for this level. So yeah, but other than that, all pretty basic. Just a stack pointer, a couple of logical things decided by whether we're popping or pushing. This doesn't have any of the fancy pushing and popping at the same time and stuff like that. No access to stack pointer. Nothing from my cool, fancy new stack register that is used in leg. But that's not required of us in this level, and what's required here is just the basic implementation of a simple stack, and I think this should be good. There's actually, if I really wanted to min-max this in terms of score, well, first of all, again, I might consider using a different type of RAM, but not this time. But more importantly, maybe not more importantly, but what I was actually going to say is this level, if we run it, you can see the stack pointer actually doesn't get very high at all. It's like, yeah, thank you. Actually, I didn't want that, but sure. It looks like the stack pointer only gets up to 1, 2, 3, 4, 5, 6. Really, it's 7. So I can reduce this a lot more if I just get rid of all these, because I don't need them. Right? And I could also use a reduced 8-bit register, and yeah, that would save me a lot. In fact, why not? This should be fairly simple. Maybe not the register, but this I can do. There. Simple as that. That's actually saves me quite a lot. This saved me 50 gates. So, yeah. Again, there's a lot more that can be done here, and maybe I will, maybe I won't. I kept this. I called it good faith because this is. I'm just making use of the fact that we are not tested on all possible inputs in order to reduce my circuit. But theoretically, I think you should expect it to be more serious than that. Yeah, but there's a couple of other things I could do. Actually, a bunch. I could get rid of these switches, and I could have, you know, just 3 singular switches, which would save me a lot. Here, here, and here. That would be, what is it? 5 times. That would be 20 switches saved. I could save on this, and maybe, possibly, even use registers instead of RAM? Nah, no way. Yeah, registers are so expensive compared to RAM. So yeah, RAM is necessary, but I would... Oh, okay, so we don't even get slow RAM for this level. So, okay, so I am not optimizing the RAM itself, and I'm not gonna go crazy and optimize this stuff, but I am aware it's possible. That'll be it for now.